Hello and welcome to this Chemistry World webinar, the pivotal role of chemistry in India's sustainable development, which is taking place today on World Environment Day. I'm Natalie Starkey, Chemistry World science media producer, and I'm here with you for the next hour, where we'll be hearing from three esteemed scientists in India working across a broad range of science focused on sustainability within their respective fields. I'll introduce them shortly. I'll just point out that this webinar is being recorded, so if you find that you miss anything today or you just want to go back and watch again, then do look out in your inboxes for a link to the recording in the next few days. Now, I don't want to take up too much of your time before handing over to our speakers today, but I wanted to let you know that as with all Chemistry World webinars, this session is interactive, which means you can ask questions about any aspect of what's covered in today's event. Please use the questions box to send in your questions as soon as they come to mind, and I'll be able to put those to our panel of guests in the live Q&A towards the end of the webinar. You won't be able to usually see other people's questions in the questions box, but don't worry because myself and the Chemistry World webinars team can, so do start sending them in soon. But without further ado, I'd like to introduce our speakers today. So I'll invite our three speakers to turn on their cameras so they can say hello. Give them a couple of minutes to find the right button to press, and then we can introduce. Hi Nishad. You can see you. Hi Suresh.
Hi.
Hi, and we're just waiting for Narpinder. I'll give him a couple of minutes and I'll get on with the introductions. Okay, I'll continue on. I'm sure he'll be looking for the camera button. It's a new software in GoToWebinar. There we go. He's appeared. Oh. Lovely to see you all. Thank you so much for joining us today. So Narpinder Singh is the Vice Chancellor at Graphic Era Deemed to be University and has a PhD in food technology. His current research elucidates starch properties across botanical sources, benefiting breeders and industry. Narpinder's contribution in metabolic profiling of crops emphasises the importance of environmental factors. Suresh Bhattacharya has a BTech in biotechnology and an MTech in fermentation technology. He has a PhD from Central Salt Mine and Chemicals Research Institute, where he is currently a senior scientist. Suresh has a strong background in biochemical engineering, and in addition, he has expertise in bioremediation for industrial wastewater through the circular economy model. And Nishad Fatima is a chief scientist in CSIR Central Leather Research Institute. She holds BTech, MTech and a PhD in leather technology. Her work is focused in protein assemblies with significant contributions on the use of ionic liquids in the stabilization-destabilization process of collagen. Her work on biophysical studies on collagen has led to the development of biomaterials from proteinous waste. So as you can hear, we've got an amazing range of speakers today with a huge amount of experience. I'm really excited to hear from all of them in just a minute. But first of all, we'd just like to take a minute to acknowledge the work of two scientists who approached Chemistry World about putting together this webinar on such an important topic. We're very grateful to them for their work during the organisation of this event, and if it weren't for them, we wouldn't be here today hearing from these brilliant and experienced scientists. Rakan Karmakar is an assistant professor within the Department of Environmental Science at Graphic Era Deemed to be University, and Pradeep Kumar Sharma is a professor and dean of environmental science at Graphic Era Deemed to be University. Rakan's going to be working in the background of this webinar alongside the Chemistry World team, so you may receive a reply from him in the questions box today. If you do have a question for a specific speaker today, then it would be great if you can let us know it's for them, because then I'll know to put it to them at the end. But if you just have a general question for the panel, then that's also perfect. We can save those for the end in the Q&A. So without further ado, you've heard enough from me now. Please welcome Narpinder on screen now, and we're going to get his presentation shared, and then you'll be hearing from Suresh and then Nishad.
Thank you very much for inviting me to share my views related to impact of climate change on food security and the nutrition security strategies needed for India by 2047. Everybody is talking about the climate change. People are talking about the water deficit, but we are moving toward desertification, we are talking about degradation of soils, and all they impact our productivity as well as the quality of material. And I will show you some of the work where we have clear-cut shown the impact of temperature on the quality as well as the productivity of wheat, rice, and herbal plants. When the climate change, it altered the temperature patterns. We have already witnessed that globally the temperature is changing, and rising temperature, it extends the growing season in some areas, but it has benefited some farmers where the temperature has gone to the optimum temperature which is required during the grain filling. But in some places where because of high temperature, heat stress has caused deterioration in the productivity as well as the quality of the product. And photo period also changes, and phenology as well as flowering, fruiting, as well as other ecosystems are impacted because of the change in the photo period. If we talk about the temperature, everybody is saying that during 1820 to 2012, about 0.85 degree temperature has increased. Now people have started that in 2024, the temperature of the earth has gone to 1.2 degrees centigrade. And if it will continue to increase by 2100, then it will be having a great impact on the yield of wheat. For example, 1 degree centigrade increase in the mean temperature lead to the reduction in the productivity of the wheat to the extent of 6%, and in rice 3.2%, and in maize 7.4%, whereas in soybean 3.1%. Now all these are the major crops like wheat, rice, maize, and soybean. Like maize is being used for the livestock, for poultry, and the population of India is already 1.4 billion. Now people have started projecting the population would be 1.7 billion by 2047. And if the population will increase on one hand, on the other hand, there is impact of temperature and it will reduce the productivity, then how we will be able to feed the increasing population by 2047. Already worldwide, the population is also projected that by 2050, the world population will go to 9 billion. So it means approximately 70% of the productivity of these major crops has to be increased. On one hand, on the other hand, we are talking about depleting or degrading soils. And already in northern India, the water has gone down to deeper and deeper. And already there is a scarcity of water. And many states, they are facing the problem of water deficit. So we have to see that we have to find the strategies in order to overcome all these issues. When we talk about the various, photoreceptors like phytochromes, cryptochromes, and phototrophins, all they play very important role in flowering, dormancy, as well as in the growth pattern, as well as in the development pattern or development response of the plants, right? So these are some of the, photoperiod plant hormones linked, right? Auxin, we are talking, gibberellin and abscisic acid, all they affect the growth of our plants like growth, flowering, dormancy, stress response, and elongation, etc. When we see if the temperature is changing, naturally the photosynthesis and carbon metabolism is also being changing. It is also affecting the carbon fixation and carbohydrates production. I will show you some of these slides where I will show the data, how it is being affected. When we talk about heat stress in wheat, right, it leads to low nutrient uptake by the roots. Then it also reduces the photosynthesis ability, alter sugars, translocation. Then it leads to the alteration in sugar and mineral remobilization from stand to grain, and it shortens the grain filling time, and it leads to the shrinkage, or you can say decrease the boldness in the grains, and ultimately affect the processing quality of the wheat. The impact of this heat stress, right, it impacts the vegetable state, reproductive stage, as well as the grain filling stage. And I will show you how it impacted. Like there is reduction in the starch, accumulation in the grain, whereas the protein content as well as the essential amino acid increase. There is reduction in the glutenin synthesis, then there is increase in the broken grains. When we talk about wheat, because when the starch synthesis is reduced, but there is definitely increase in the proportional protein content. When we see in the context of malnutrition or protein deficiency, it's good sign, but the processing quality of wheat deteriorated because of the in India we consume chapati where large amount of or high content of protein is not required. So because of this high accumulation of the protein, elasticity of the dough increases and the quality of the end product, that is the chapati, is deteriorated because of this. If we see the bread making quality because of the high protein, damaged starch, it definitely improves with the heat stress because of Indian wheat varieties. They have medium protein, weak gluten. So when there is a heat stress, thus in some of the varieties, the protein content increases. But of course, the starch synthesis, many enzymes which are involved in the biosynthesis of the starch, they are impacted because of the high temperature. There is also decrease in the mylose content, whereas there is increase in the synthesis of gliadin, like heat shock elements. So definitely, I will show how the quality of the protein, how the reduction in the starch content impact the processing quality of the various grains. So when heat stress is high, the grain gets shriveled, hardness is more, gluten strength is also increased. Sedimentation value, which indicates the protein content, also goes high. The pasting properties, that is how the starch gets gelatinized, all these pasting properties, they have the link to the end products like baked product, like cakes, muffins, and bread. They have a direct impact. But it is also found that when the high temperature is there, the alpha amylase activities also decrease. The rheological properties like absorption, dough development time, they are all related to the protein content. They also improved because of heat stress. So we have carried out some of the properties like in order to see the impact of climate change, we basically change the transplantation date. So we have the timely sown wheat, which is usually sown on 15th November. Then we delayed the sowing of the wheat to the 12th December in order to see the impact of temperature on the quality of the wheat. So delayed sown wheat, usually if you see here, when we sow here in the month of November, the flowering takes place here when the temperature is lower. But when you sow here on 16th December, the temperature at the time of flowering is high. So this high temperature is basically impacting the quality of the wheat. So we have changed the sowing period in order to see how the temperature impact the quality of the end product. So you can see here that delayed sown wheat, it has 17.4 degrees centigrade and 23.7 degrees centigrade, the mean temperature, maximum, mean, and minimum and mean temperature. But in case of the timely sown wheat, you can see there is 23.29 degrees centigrade and 16.1 degrees centigrade, right? So this is the difference in the temperature. So if you delay, it means there is heat stress because the flowering takes place at high temperature. Whereas if you timely sow, the temperature is lower, you don't have the heat stress. So we want to see the impact of heat stress. That's why we delay the changes in the sowing period, right? So this also impacts the height, like the heat stressed wheat, that is delayed sown wheat, has the lower height. Then the days of flowering also lower, and then the plot yield also is reduced. That there is a decrease in the yield up to the extent of 28, 37 or 38% because of the heat stress. Then we also check the grain hardness. Like you can say the grain hardness also is difference. This is the grain diameter is reduced because the grains were shriveled in the heat stress condition. The grain hardness was more because the grain was shriveled. 1000 kernel weight also decreased with the heat stress conditions. So the color values, the whiteness of the flour which is produced is also lower in case of heat stress conditions, and this whiteness is required to be higher in case of we consider the quality is better when the whiteness is more. So this also reflects the difference in the protein content. Heat stress wheat has high temperature because there is less starch synthesis, and you can see the protein is more in most of the red, the bars. They are heat stressed wheat, so they all impact. Wet gluten is also reflect about the protein content is more in case of stress wheat. Dry gluten also reflect the same. Gluten index also indicate related to the gluten quality. Water binding is related to protein. That's why it has more water binding in case of heat stress. The grain structure was very hard. If you see, this is the heat stress wheat. This is the normal wheat. Heat stress has a high nitrogen percentage, which is clearly reflected by the high protein content. So you can see the structure is very distorted, very hard, and it also impacts the milling processing at the commercial level, right? If you see that the storage protein, they also change and they impact the quality of your flour. The paste, I have already mentioned that late sown wheat has, the high, you can say the paste viscosity because of the difference in the alpha amylase activity. These phrenograms basically tells about the gluten strength. You can see the stressed wheat has more stability in case of gluten or dough as compared to the timely sown wheat. So this clearly showed that the wheat, Indian wheat particularly, becomes suitable for bread making, but the quality of the chapati making got deteriorated. If I see the rice quality, it is already mentioned in many research articles that the climate change is going to impact the various, the nutrients. Like you can see some of the nutrients, they have shown to be increased, but most of the nutrients, they are impacted by the protein. Again, we carried out some experiment with the rice in order to see the temperature impact. Like again, we grow early transplantation and delayed transplantation in this in rice. We did it, and you can say 5th June or 15th June and 25th and 5th July. This is the delayed transplantation. But in case of rice, it is other way around, right? When you early transplant, then the temperature is cooler. But when you delay the transplantation, for example, if you have here, right, you grow here, the flowering takes place somewhere here, and if you, in case of July, the temperature goes down, right? So you can see date of transplantation also impact the 5th June. When you have the 5th June, the temperature is more, but when you grow in July, the temperature decreases, right? Now, it is other way around that we need the cooler temperature at the time of flowering. Here, the temperature is more, you can say. When we delay, it happens in September, somewhere the temperature also decreases, right? So the temperature at the night, play very important role in the synthesis of the starch. So you can see that if we grow at 5th June, early transplantation, then you have the heat stress and you have the lower productivity. But when you delay, for example, on 25th June, because then you will have in the month of September in case of the grain filling. Here you will have in the month of August flowering. So in August, the temperature is more, whereas in the month of September, the temperature is lower. You clearly see from 61 quintal per hectare, the yield has increased to 73.5. So we have suggested that the delayed transplantation of paddy is always good, because at the time when you delay, you have the monsoons and the temperature has also go down and there is less load on the electricity. So we need to have the strategies by manipulating the growing condition in order to have the minimum depletion of water and minimum use of electricity during the productivity of rice. So again, you have more chalkiness when you grow early, when there is a heat stress, more chalkiness, more breakage of the grain. And again, it is happening that when you have the less heat stress, more starch is produced. And when more starch is produced, you have better quality rice, more amylose and better, resistant towards the breakage. So
Sorry, Nalpender, Sorry, we're just about out of time. So you've got one more minute if you can summarize fairly quickly. Thank you.
Okay.
Sorry to interrupt.
So basically, all these wheat grass and everything, there is a great impact of the climate change. So we have to make the strategies. We have to optimize what is the right temperature so that you can have the optimum temperature at grain filling, so that you have the good quality wheat or rice, because climate is changing, the growing conditions are changing, and we have to change the transplantation, sowing, harvesting, and we also need to develop the heat resistance variety so that they can tolerate any rise in temperature. So thank you very much.
Thank you so much. Wow, so much information now. I'll remind the audience that this webinar is recorded, so you can go back and watch again. We'll be able to send you a recording in the next few days if you've missed anything or need to go back and check again. Thank you so much, Nalpinder. We're going to come back to you at the end in the audience Q&A. What I'm going to ask is Suresh to turn on his camera now. He's been having a few little network issues this morning, so bear with us if Suresh's camera drops out or audio a bit. We'll try and work around the issues, but we're going to try and share his screen now. So we'll give him control and hopefully that will work. I'll let you take it away. I'll let you know if there's any problems, and I'll come back on around 12 minutes for the next speaker. Thank you.
Okay, so a very good afternoon to all of you. I know today is the World Environment Day, and now we are very cautious about the environment. One of the reasons that we have become very cautious is the issues of climate change, and means for the carbon emissions, means not only the flue gases and other sources are there, but also means we are using the fuels to a greater extent. So that's why I will be telling few of our processes that we have developed in relation to microalgal biofuel. So coming to the main slide, we all are literally worried about the flue gases that are being emitted at large scale. So here comes the one of the best solution, that is the microalgae. So microalgae can take up the CO2 from the flue gases, as well as it can also grow in the SOx and NOx conditions, and simultaneously it can also utilize the wastewaters and grow very well. So we all are aware of the industries like coal-based industries, because if we are thinking of the electricity from the thermal power plants, coal-fired power stations are there, then we have underground coal mines, and simultaneously there are a lot of industries which are releasing a lot of wastewater into the environment. So our processes are based on microalgae based processes, wherein we can grow microalgae in the CO2 which is being present in the flue gases, and simultaneously the wastewater can also be utilized for the cultivation of microalgae, which can result in various products starting from animal feed, obviously biofuels, biofertilizers, nutraceuticals, and carotenoids. So how we take a call which strains need to be collected, or means how to proceed on and far as industrialization is concerned. So basically, initially we will select a potential strain that can grow in wastewater, as well as can take up the CO2 from the flue gases, and simultaneously it can remediate the heavy metals and other things, as well as it can produce the nutraceuticals or other products. So the cultivation strategy is concerned, we have open based system, like we can cultivate in open ponds, then raceway, then some of the industries are also cultivating microalgae in the vertical bags, and obviously photobioreactors or fermenters for heterotrophic cultivation. So these are some of the systems that is being used. So basically, our journey started in the year 2010, where apart from CSIR, CSMCRE, there were 8 to 9 partnering institutes were there, starting from IICT Hyderabad, NIO Goa, NCL, NIST, IIT Kharagpur, NIOT, Calcutta University, and Andhra University. So during this project, we have gone completely on the coastal area, and fortunately we were able to identify a potential strain that was halotolerant and thermotolerant, and it can produce the oil at any temperature or at any salinity. So, so during the journey, what happened? We can't develop the process instantaneously, and there was a need. So we have gone into the nature. We have collected some of the microalgal mats, and oil were produced from those microalgal mats. And then we are able to run an B20 biodiesel during the year 2011. So this generated a proof of concept that it was possible. Here you can see that means the microalgal mat regrowth was there, means we are not disturbing anything in the nature simultaneously. So then in the next approach, as I was telling you, we were able to identify a potential strain which was halotolerant as well as thermotolerant. So then we cultivated in open ponds, not the raceway ponds, because raceway ponds are cost intensive process as well as energy intensive process. So what we have done, we have utilized the unutilized land of our experimental salt farm, just dig the land, put the liner and grown the microalgae. And this microalgae doesn't need much agitation, and we were able to get highest biomass productivity, which was something around for 45 to 48 gram per meter square per day, and which is auto settled in nature. So we don't need any centrifugation process or any dewatering technology. After 10 to 12 days, the algal biomass can be settled down. It can be taken off and then dried, and from that oil can be produced. So obviously the factors that were important for microalgal cultivations are light, temperature, pH, type of algae, aeration, mixing, and obviously photo period. So basically there are three cultivation strategy. One is the batch process, another is the semi-continuous process. It is easy to handle, but it is less reliable or sporadic. And simultaneously, most of the industrial process runs on a continuous mode, and it is more efficient process, but there are few disadvantages, like sometimes the equipment cost and other things are high. So this is the basic mass cultivation fluxogram. So basically during the initiation of the mass cultivation, first we need the seed material. So we generate the inoculum at a scale of 1 meter cube, which is further transferred to another pond, something around 5 meter cube, which is having a batch size of 15 to 20 days. So when the OD reaches, let's say 0.9 to 1.4, then we transfer that inoculum to a pond which is much bigger in size, at a scale of means 10 to 100 times. So let's say from 5 meter cube, we can proceed to 300 to 500 meter cube, and this microalgae is having a batch size, something around 12 days. So what will happen on every 12 days we need to harvest the culture, and the water can be returned back, and the biomass can be subjected to drying, which would be further means oil would be extracted from it in the Soxhlet extraction system, and followed by various bioproducts. So then sometime around 2012, we were able to run an unmodified diesel vehicle with this neat microalgal biodiesel, which cleared the PUC as well. So then we have also validated our microalgal biodiesel with various parameters as compared to the diesel. The diesel is there, and we can see the CO2 emissions were quite low. Not quite low, but it is in the comparable range. So these were various media coverage were there. So during the process, there were some lessons that we have learned. One, first and foremost, is that during the open cultivation, environmental fluctuation was there, and that environmental fluctuation sometimes lead to towards the decrease in the oil content in the microalgae. Sometimes airborne contamination were also there. Then the energy output to input ratio, as means with the conventional oil extraction, was less than 1. So then we have implemented solar based oil extraction system, but again scalability was the issue. Seasonal variation of the lipid in large scale cultivation was another issue that we faced. So the critical things that we found is that we were able to do the natural harvesting through getting the auto settled biomass. Simultaneously, we have identified a best strain of chlorella, which can grow in 3 to 8% of salinity, as well as it was thermotolerant, which is having 25 to 45 degree Celsius. We have utilized seawater for our cultivation. During the journey, we have also developed a product called dry sea mix. From the brine solution, we have prepared prepared this product dry sea. Means, for example, in the places where sea is not there, they can directly add it in water and get the composition exactly similar to pristine seawater. So obviously, these processes have societal, economical, as well as environmental impact. So we have tried with the solar-based offset extraction system. This, you can see our pilot setup for oil extraction. So then simultaneously, then the question comes, what during the biodiesel process there were crude glycerol were diluted. So then we have developed a process for bioplastics wherein this crude glycerol were utilized for developing PHAs. These were the optimum conditions. So during this journey, we have noticed another point is that key water footprint needs to be reduced. So then we have moved to one of the very challenging task wherein bioremediation of textile wastewater was an issue. So then utilizing this algae, we were found that we are able to remediate the heavy metals as well as dye content in the textile wastewater. Obviously, it was taken from cotton-based textile industries. So here you can see the treatment cost was something around 2.5 rupees per meter cube, and the biomass production costs were also reduced to 10 rupees per kg. So from this biomass, we can extract initially the total lipids, which is having PUFA fraction, so that can result in gamma linolenic acid, and simultaneously the non-polar fraction can be converted into the biodiesel, and then the whatever the de-oiled biomass was left over, so we can produce biopolymers, which involves bioplastics as well. And also we have developed a process for a very innovative polymer, epsilon polylysine, which is a natural food preservative as well. And here you can see that the completely remediation of color was obtained, and this was published in ACA SUSCHEM long back in 2017. So this is the complete material balance of this process. As I was telling you, we were able to produce some of the products with utilizing the residual biomass. But what happened generally is that whenever we are doing any hydrolysis, either it is acid or it is enzymatic based. So enzymatic based are not cost effective, and acid based process have certain issues. So we have utilized normal detergent, that is SDS, and we have developed a process for SDS mediated hydrolysis, which gives us quite good amount of sugars in it, and the hydrolysate containing more than 7% of sugars were subjected to bacterial fermentation, and wherein one of a very important product, that is epsilon polylysine, which is having a lot of medical applications, can be produced from it. So utilizing that hydrolysate, we have extracted this epsilon polylysine, which was later purified using ionic liquids such as ethyl ammonium nitrate. This was the scheme of the process. So then comes another, this is a spin-off process of our previous process, wherein the GLA, gamma linolenic acid, was purified and developed into a product form. And this gamma linolenic acid is a very important product for women health, because it is being used for treating PMS in women. This is the material balance fluxogram, and whatever the process was developed was very cost effective, which is costing something around 890 rupees per liter. And if you see the market cost, it is double of that. Recently, we are transferring this technology to Abbott Biotech. Okay, another bioremediation process was the bioremediation of wastewater, fishery wastewater. So basically, in Gujarat, there are a lot of fishery-based industries. So we got fishery wastewater, which is having a lot of various content, not in terms of metals, but it is having a lot of protein and other carbon content, which we found a potential feedstock for our microalgal growth. So we have utilized fishery wastewater directly for cultivating Chlorella vulgaris, and after 12 days we found that the utilizing this biomass we can extract 3 major products, one of which was obviously astaxanthin, because it is having ammonium content in it, and during the cultivation of the microalgae, lot of stress is being develop, which is leading to production of astaxanthin as well. So we can recover astaxanthin, and the residual the oil can be subjected to biodiesel production from the non-polar lipids, and obviously whatever the biomass is there can be subjected to bioplastics production. This is the overall cost, economics, and material balance of this process. So simultaneously, when we were developing the bioplastics from the hydrolysates, so we think that why not to utilize fruit glycerol as well. So then we have developed a process wherein residual microalgal biomass can be subjected to hydrolysis, and the hydrolysate containing sugars. Along with that, even the biodiesel waste residue, fruit glycerol, can also be utilized for the bacterial fermentation, which can produce 2 products, that is epsilon polylysine, which is a extracellular product, and polyhydroxyalkanoate as an intracellular product. And the main aim behind developing this process is that if we are able to produce 2 simultaneous products, this can be the overall cost of the process can be reduced. So this is the optimum conditions for the epsilon polylysine product, and we are able to get epsilon polylysine yield around 0.2 gram per liter, and on the other hand the PHA yield was 64.6 percentage with respect to cell dry weight. And even as far as downstream is concerned, the purification of the complete process was a single step purification, wherein we can directly precipitate the polylysine utilizing tetraphenyl borate anion. These are the analysis. So that's all. These are our collaborators, and we have a small group at CSMCRI.
Thank you so much. That was brilliant. Thank you. You've covered a lot of information there. We've got some questions coming in from the audience, but I'm going to save those for the end when we'll get you back, because I'd love to hear now from Nishad, who's our final speaker today. So we'll welcome her on screen. There we go. We've got you. Lovely. Perfect. You've got it. I'll let you take it away. Thank you.
Right. A very good day to one and all present there. The title of the talk is Tannery Waste into Value-Added Products, a Route for Sustainability. Now, before going on to talk about the value-added products from the tannery waste, I would just like to tell you that skin, the raw material for the leather itself, is a waste from the meat industry. So this waste of a meat industry is being converted into a value-added product, and trust me, the value addition is so much so that several products with the uniqueness which the leather offers are being made. Just to give you an overview of what this leather processing is all about, it is converting a putrescible raw hide or skin into a non-putrescible leather. So if I leave the skin as such, it is going to decay because it is a proteinous matter. But if I convert it into leather, it is going to remain forever. And it truly connects a rural farmer with the fashion world. When I say this, leather itself is, today in the fashion world, it is one of the most sought after material. Just to give you an example, the various products which you can make out of leather, of course, being a lady, handbags first. And everybody knows the leather footwear is one of the most sought after items. The garments, And there are several other accessories which we can make out of the leather. What many may not know is that it also has several industrial applications like the sharpening leather, the belting leather. For the textile loom, it is used as a picker. Sought after for cleaning as well as for oil filtration purposes. And where does these properties stem from? Because the origin, the natural material skin, the raw material which we start with, is truly an architectural marvel. We actually remove the epidermis and the hypodermis, and it is only the dermis which is actually converted into leather. And this comprises of a protein which is called as collagen, and collagen has uniqueness in itself compared to other proteins, and this renders the leather the different properties which are unparalleled, unmatched by any other man-made fabric. Now, having said all these good things about leather, it also turns out that when I convert, say, a ton of raw hide or skin into leather, about 700 to 750 kilograms of wastage is generated in the form of solid waste. Now, the question is, what do I do with this waste? Yes, I'm converting a meat industry's waste into a value-added product, into leather, fine. But at the same time, in this process, I'm also generating some amount of other solid waste. And yes, if you want to talk about environmental sustainability, the question we asked ourselves was, can one man's trash be another man's wealth? And why should we worry about this? Why should we ask this question to ourselves? Because we have to save the planet today. And on June 5th, 2024, when we are celebrating this World Environment Day, this cartoon, kind of tells you on the Earth Day on 2035, you don't want to stand in front of a picture of a tree, rather in front of a tree to do this. And these are few cartoons which, tell us that environmental sustainability is no longer the buzzword or keyword. It is a mandatory thing which we have to address today, especially when you see here, this man holding a placard, someone do something about climate change. And he asked this little one, what are you looking at? And she says, that's someone. So what we did was, can we take this solid waste and use it to treat a liquid waste? Now, this sounds a little strange, but I'll come to it. When we talk about liquid waste, this dyes and chromium-6, in fact, chromium-6 doesn't come from the leather industry. It is only chromium-3 which we use and which is not toxic state. Nevertheless, chromium-6 does come from the electroplating industries, and dyes, textile industries are the main culprits. So you do have liquid waste on one hand, and we have this tannery solid waste coming on the other hand. Now, what we thought to ourselves was, can we put together both these wastes? There is a liquid waste problem, there is a solid waste problem. Can we combine these two problems and actually find a solution? Well, it sounds like we are talking against the mathematical principles, but yes, how did we achieve it? Through very simple chemistry. This seminar is to see how chemistry can enable sustainability. So this is what we did. We know that this is a proteinous waste, and proteinous waste means it has a lot of functional groups, including the carboxyl group, which is present in this collagen protein. So we took iron and we complexed it. It forms a coordinate covalent linkage with the carboxyl groups present in the protein. So it gives you a cationic center, and this cationic complex can now attract or absorb the anionic chromate ions. Simple, it's done. Similarly, we did it for the dyes as well, and you could see here from this figure that we were able to remove about 95% of both dyes as well as chromium-6. But the question is, have I now solved the solid waste problem? I have solved the liquid waste problem. I have removed the toxic pollutants from the liquid or the wastewater. But did I now solve the solid waste? It is now more compounded because my tannery solid waste now contains both this dyes as well as the chromium-6. So what we did was, I told you this is proteinous waste. So that will act as a good reducing agent in the manufacture of basic chromium sulfate, which is a tanning salt which is used in leather industry. And thereby we converted a waste into a value-added product, and reused it back in the leather industry itself. So solid waste plus liquid waste resulted into a tanning salt, an efficient way to manage the solid waste. Next, another application was to look at solid waste as rubber soles. Now, we all know that when you make a rubber, generally carbon black is added as a filler material. To every 100 parts of rubber, we in fact add about 50 parts of carbon black. But we thought we will convert this waste into activated carbon, and instead of this carbon black, we use this activated carbon, and we were able to get the material equivalent, if not better, than the conventional methods. And this is another example of converting a waste into wealth. To give you just an indication of the numbers I'm talking about, annually about 50,000 tons of flushing waste comes from India alone, and you can make about 2,000 tons of activated carbon. Even if I don't convert the entire waste, I just even take 25%, as the waste to the conversion to activated carbon, you will have 500 tons of activated carbon. And there are ample applications of activated carbon, including what we just told you about converting it into rubber soles. It has dual benefit, both for the tannery as well as for the rubber industry. What is that for the tannery? It avoids the disposal of the flushing waste into the landfill, obviously, because you're converting it into a valuable material. Not only that, you gain revenue out of it, and nevertheless, it reduces environmental pollution. Now, what are the benefits for the rubber industry? You avoid the usage of the so-called carcinogenic filler carbon, and you get a very good vulcanized rubber. These are few articles which came up about our technology. And if you could, I don't know if the figure is able to do this justice, you can see here that the control, compared to the control, the sole, the experimental sole is more black in color. So that shows, the kind of material we have made. Now, this carbon, we thought, why can't we convert it into a super hydrophobic carbon and use it for oil water separation, because that is again a major challenge which the world faces today. So we developed this super hydrophobic carbon from the tannery waste by doing pyrolysis at 400 degrees, and you could see here that how the water contact angle is for the normal melamine sponge is 0 degrees, and once you coat it with this carbon, it ends up being super hydrophobic with 158 degrees centigrade. And these are the few characterizations which we did. I'm not going to bore you with the details, but the efficiency with which this material works is amazing. Just to show you a small video here, we have colored the toluene here to show you, because toluene is colorless. So just to make you see the difference, how it is able to remove the oil and separate it from the water. So on the left, we have the native or naked melamine sponge, and this is our hydrophobic carbon coated material. You could see here how very nicely, quickly it is able to remove the solvent or the oil as such from here. So what I'm trying to tell you here is we do have endless possibilities, applications for converting this solid waste into value-added material. Now, one other application we looked at was, can I convert this solid waste and use it for a product which will reduce yet another pollution? Remember, first one was treating a liquid waste problem. That's one form of pollution. We also know that noise is also a pollution. So we converted this into nanofibers. We know that because of the nano topology, the surface area increase leads to a lot of advantages. And we did make this nanofibrous mats along with the other composite polymers, and we have been able to reduce the pollution to a very large extent. So what I'm trying to convey at the net, at the end, is that the tannery solid waste is a new raw material for making number of products, like the basic chromium sulfate to be used in the leather industry itself, as an activated carbon which goes as a filler, as the super hydrophobic carbon for oil water separation, or as an electrospun nanofibers for sound proofing. So there can be n number of such value added products which can be generated from the tannery waste. Why should we worry about it? Because the linear economy is not going to be the way forward. It is the circular economy. Why? Because it will only result in zero waste. So what is the take-home message? Well, Mahatma Gandhi ji has said, be the change that you wish to see in the world. Remember that small girl in that cartoon who was looking for that someone? Well, that someone is you. If every individual believes that he or she can contribute, it doesn't have to be a scientist. You can be a normal individual at your, in your space. You can do wonders and save the climate, save the planet, save the environment. Believe in yourself, and trust me, it all starts with you. So thank you for the opportunity. Our institute's motto is doing better today than yesterday and forever. All the best. Thank you.
Thank you so much. What a lovely message to end with the presentations as well. Thank you. It's very inspiring and great for World Environment Day. But absolutely fascinating. All those things that you can do. I don't know how your brain has gone to all those different ideas of, what on earth can we do with this product with so many different uses. But that's absolutely fantastic. Thank you. Again, to the audience, please keep sending in your questions. We've got a lot coming in now. For all of our speakers. So I'm going to invite Narpinder and Suresh back on screen now. If you want to find your camera button and your audio button, and then hopefully we'll be able to see and hear you very soon. We've got, as I said, we've got some questions coming in. I'm just going to have a look at this one for Nishad whilst we're waiting for the other two to join again. Okay, so this question, actually Nishad, it says, any comments on how much is the water usage for the processes? The leather industry is notorious for water intensive processes. Great question.
You are absolutely right. While I was talking about the solid waste which is coming out, we do generate a lot of wastewater, in the sense liquid waste as well. The industry world over average is about 20 to 25 liters of water per kilogram of the raw hydro skin processed. But I would also like to highlight here, in fact, in Tamil Nadu, the place where I am working, we practice zero liquid discharge, which means the entire water which goes into the process is actually treated and reused back into the process. So we have a concept of zero liquid discharge. So while we, it is notorious or it is famous or, people do know that leather industry pollutes, but today we have technologies in place which ensures that we do not cause any environmental concerns.
That's brilliant. That is good to hear. And as you say, that's the way forward, isn't it? We've got to take on these sustainable approaches. So that's really good to hear. I'm going to go to Narpinder next. I've got a question for you. Hopefully we can hear you now. A great question about, many of the agricultural lands in India are getting more barren over time. And one question is, can the chemical changes in these be restored? Is this something that you're working on or something that can be achieved?
Pardon, I have not understood. What was the question?
So can the chemical changes in barren lands in India be restored as climate change and the use of the lands for agriculture is depleting them of their chemicals? Can you restore those changes into the barren lands?
Yeah, actually it's a very challenge because now we have 1.4 billion people, right? And by 2047, 300 million people we are going to add, right? And we are harvesting, we grow wheat, then we harvest wheat, then we sow rice, right? In order to feed our ever-increasing population. Sometimes we have the three crops, right? It is a great challenge, right? Because to feed the population, soils are depleting and it's very difficult to answer how we will overcome in the next 2047, how we will increase the productivity to 70%, right? We still need to improve, the yield, and we have to develop some varieties which are high productivity. We have to optimize, as I earlier mentioned, the sowing condition so that our productivity remain, at least if it will not increase, should not decrease because of change in climate. We need to develop more varieties, and we have to efficiently use some more cultivable lands, right? Has to be included for cultivation of, the crops. So these are the challenges, and we have to find out the ways.
Excellent. I'm glad we have people working on this.
Urbanization is increasing, the land, more and more urbanization, we need more houses. Construction is going at a very fast rate. And population, we have to control the population also in order to get, this is the great challenge.
Absolutely. Well, thank you so much. That's a great insight into that question. Thank you. Suresh, we're going to move on to you. I've got a few questions actually about the cost of the microalgal biodiesel compared to other biodiesels and even conventional crude oil. Could you give us any idea about kind of the cost per litre or just a comparison of those kind of costs of those?
Yeah, actually at this stage, whatever the costing we have done, it is costing something around 125 rupees to 130 rupees per litre. But again, this process, the process is getting refined because that is at this stage, we know the petrol cost is quite high. So in such scenarios, we need to slightly reduce the cost, and we are working on it. Means I have shown the biorefinery model. Currently, we are working with two industries in India. One is the Tata Chemicals and another is the Adani Power Limited. So right now, what we are doing, we have already developed a POC, and we are going slightly on a manufacturing scale in collaborations with Adani Power Plant, which is located at Mundra. It is the largest coal-based thermal power plant. So we have developed all the setups. Now I think by the end of July, we will be taking the batches wherein I think we are targeting something around 1600 kg, means at least 10 to 15 LPD, liters per day, so that we can come at a realistic cost through biorefinery model. Means what we are doing there, whenever we are taking the oil, we are also generating the nutraceuticals. Like in the process, we are taking the total oil out of it, wherein the non-polar fraction can go for the biodiesel production, and the PUFA content is being purified, which would be sold to the nutraceutical sector, and the residual biomass will also go for animal feed purpose. So we have developed now a sustainable model which will reduce the cost to within 100 to 110 rupees per litre.
Thank you very much. That's a really good answer.
We are also working on the aviation fuels, because the problem is that with the biodiesel, it will not going to solve the issue, because the CO2 there in the air is quite high. So it is not coming only from the let's say from the emissions, however, means from vehicle emissions or from the power plant. The aviation fuel is also playing a major role. So recently, I think we have a policy in India where 5% blending of SAF would be there in all the aviation fuels. We have last year I transferred tech to Tata Chemicals, and now we are working closely on developing microalgal based sustainable aviation fuel, wherein we would be able to blend at least 1% to the aviation fuel. That is their aim of Tata's. So these were the things we are working on. So we are hoping that by next 4 to 5 years, we will, means India would be at a good position as far as environmental sustainability and climate change is concerned.
That's really good to hear. Yeah, no, I'm loving hearing the range of work that we've seen today, and it gives me hope that we've got good scientists working on these really big problems. And I think, as you've all shown in your presentations, each of your respective fields in itself is massive. We've got big problems across many different areas, and I'm loving that we're hearing so much new work that's happening. So thank you so much. But I just want to say a big thank you to all of our speakers today. For anyone watching, if you need to go back and rewatch, it's all there. Nishad, I'll let you know that your internet did cut out just briefly during your presentation. So we lost maybe one slide, but I think we were okay. It was actually fairly near the start of your presentation, so we were absolutely fine. I think everyone kept up anyway, so that was fine. But thank you so much for everyone joining us. And we've had some brilliant questions coming in, really broad topic as you've seen, and very complex, but I think it's given us a nice positive day today to think about World Environment Day. So thank you for joining in. Thank you for being here. If you've enjoyed this webinar, then please do check out chemistryworld.com/webinars for any future events. We've got quite a lot of webinars coming up. And while you're there, you might want to register for a Chemistry World account, where you can sign up to our very popular Reaction newsletter that includes a weekly digest of big stories from across the whole world of chemistry. But from everyone here at Chemistry World, we look forward to seeing you again in a future Chemistry World webinar. Thank you and goodbye.
Thank you.